Lesson 21, Universal Gravitation. Okay, so I assume most people have heard of the word gravity. And you probably think, well, that's pretty simple stuff. It's the stuff that, like, pulls you down to the ground. But for the longest time, we had no idea what it is. And actually, I shouldn't even say for the longest time, we still don't have a good grasp on what gravity really means. But, we can approximate a lot of it. And yeah. So, this goes back to a story. So, we got the story of a guy named Kepler. We're going to talk more about him later when we start talking about the motion of planets. He analyzed the motion of the planets, right? He took the data from a guy named Tycho Brahe, and he was able to take that data and he made up three laws. So he made up, you know what, I'm not going to go too much into them. You can read through those. We are going to go through that in lesson 22 anyway, so I'm not going to spend too much time on that. So up until this point, Kepler was able to explain why the heavenly bodies or the planets in our solar system, why, or actually he didn't say why, he just was able to give a mathematical approximation of how they work. So we could say if some planet is at this point in the solar system and this is our sun, then he would be able to figure out, 300 days later, that planet's going to be over here. And he could figure out where that would be, right? But he wasn't able to say why. So just like when we were talking about circular motion before, when I had a string and I was like had my keys spinning around in my string, that's pretty straightforward. There's a string that's attaching those two, right? And in that case, I was the centripetal force, or the string was the centripetal force pulling it in. But when it comes to one planet and another planet, what's actually pulling it together? To Kepler, planets were somehow he figured maybe magnetically driven to the sun. It was like this invisible thing that nobody really understood. It wasn't until Isaac Newton, and you've probably seen or heard of that famous incident where he's sitting under a tree and an apple hit him on the head. He never really talked much about that, and we're not even really sure if that happened at all. But he was from that moment, if it did happen or not, he was able to think of this notion of something called universal gravitation, and the idea is that there is an attraction between anything with mass. So two objects with mass, whether that's you and the person sitting beside you, or a planet and the moon, there is an attraction between them. So Newton set out to try to figure out some sort of equation that could actually explain this thing that's actually happening here. And they said, why does gravity seem to be diluted the farther out you go? So the force of gravity, I forget what it is. Yeah, if you're comparing an apple falling toward the Earth and comparing the gravity of the moon being attracted to the Earth, it's actually the gravity of the moon being attracted to the Earth is 1 over 3,600 that of the acceleration of the apple. So the acceleration of the apple is way more. But why? And sorry, I misspoke there. Not the force. The acceleration of the apple is that much more than the moon. And if you think, or when they did think about it, it's actually all to do with the distance. So the moon is 60 times farther from the center of the Earth than the apple. So if we take the center of the Earth, right, and that's where we kind of have to measure things from. So if we've got an apple sitting here, and we got the moon out here, that moon is 60 times farther away than the apple, right? So what they were able to figure out is that, well, if I go 1 over 60 squared, so 60 to the power of 2, that gives me my 1 over 3,600 times that of the apple. So it's all about the distance, and the distance is squared. So force, so let's go down here too. So Newton concluded that the relationship between the force of gravity between the Earth and any other object and the distance, which separates their centers, and that's important, right? It has to be the distance from the center of one thing to another. You wouldn't say that if the apple was sitting on the edge of the Earth here that the distance was 0. You have to take into account the radius of the Earth. Can be expressed by the following relationship. So F And then remember, this symbol means proportional to 1 over distance squared. So now again, thinking in terms of equations here, if I look at the distance, so let's say that the force was like, 1. So pretend I had like 1 in place of the force there. And the distance here was 1 of whatever unit. Now, let's replace the distance. Let's replace it by 2. Now really what I've got here is 1 over 2 squared, or 1 over 4. So the force of gravity here is a quarter as strong. So every time the distance goes up by 2, it's squaring it. So it's 2 squared. So you can see how this drops off really fast. So the force of gravity is going to drop off really fast when it comes to the distance. So if you put in a different number, just to give you like a bit of a sense there, if I put in 3, so for distance I put in 3, well, I'd have 1 over 9. So now just going 3 times farther away, my force of gravity is 9 times less. If this was a 4, it would be 1 over 16. So now I've gone 4 times farther away. Now my force of gravity is 1/16 as strong as it used to be. This phenomenon is called the inverse square law. And this is going to come up in other fields as well when we take physics 30. You guys are going to see the inverse square law for some other forces as well. So that just has to do with how the force of gravity drops off with 1 over the square of the distance. So Newton knew that the distance made a difference, and he had the beginning of an equation, 1 over d squared there, right? That wasn't equal to, but proportional to. But he knew that there was also something else that affects the force of something, right? He knew that the mass affects the force. So force is equal to mass times acceleration. So we knew mass was involved, but he didn't. But which mass? Like if this was an apple we're talking about, are we talking about the force of the mass of the apple, or are we talking about the mass of the Earth? Well, it's actually, they both need to come into account. So if I had the apple and then the Earth, remember with Newton's third law that if this apple falls down toward the Earth falls up toward the apple. So both of these masses need to be taken into account. So we knew that mass was involved, and he also said that it applies universally. So it's the universality of gravity, or the universal law of gravity. And the big deal here is that all objects attract each other. So technically, I'm gravitationally attracted to, some alien in the distant galaxy. It's almost infinitesimally small. It's a hard word to say. But I am attracted to that alien. Oh, that sounded weird. Okay. Anyway, so he figured out that he knew that the distance, if I want to figure out what the force is, it's inversely proportional to the distance. So he has distance in the denominator, and it's squared too, right? Because it's inversely squared, or inversely proportional. And he knew that it went up as the masses went up. So you get a bigger mass, you get a bigger force. So they go up in the numerator. And then we just need some sort of constant. And this constant is called big G. It's the universal gravitational constant. And it really is universal. So this constant is actually like embedded in the universe. Like this constant is something that apparently, no matter where you go in the universe, this gravitational constant would be the same. It's actually, just to get off track a little bit, this constant and a few others in nature, a big question in physics right now is, why is this constant what it is? It's 6.67 times 10 to the negative 11, and then here are the units for it. But why? It seems like that was just such a exact number. Could it have been anything else? We don't really know. And that's one of the questions that a lot of people are looking into. So, in order to figure out that number, though, I guess Newton didn't just come up with that. There was a guy named Henry Cavendish. He conducted an experiment, and you guys can look at the experiment in page 205 and 206 in Pearson. This constant, just so you know, I'm going to show you on your formula sheet here now, is on this side. So universal gravitational constant, and that's big G, 6.67 times 10 to the negative 11. So yeah, and you're also going to need the mass of the Earth and the Earth's radius and that kind of stuff now. So keep track of that. Okay. Now, really, these examples shouldn't be too difficult. They really are just like plugging in the numbers. The only thing you might have a problem with is putting things into your calculator. So we've got these like giant numbers that we're going to be dealing with. So scientific notation. Make sure that you know how to put those in. So look at some past videos to make sure that you do that. And in your calculator, use the EE button. That's going to make things easier because that makes when you use that, it's letting your calculator know that you're talking about one number. You're thinking about this thing as being one number, not two. So if you go times 10 to the negative 11, your order of operations might get mixed up. So the force of gravity between different planets that we're going to be talking about, like planets or galaxies or anything like that, they're very small. 2 times 10 to the negative 6 was the one for that question up there, right? Um, and especially if we're talking about things that are, just the size of, like a tanker or a super tanker, right? Like these things that we think about as being like really big. The force of gravity between them is very small. You have to be talking about things with huge mass to get significant amount of gravitational force between them. So go ahead and look at example number 2 here. Again, we're going to have to be able to rearrange formulas properly. And yeah, I'll let you guys look through that one. So let's look at example number 3, though. It says a person with a mass of 100 kilograms has a weight of 981 newtons on the surface of the planet. What is the person's weight at a height of 12,000 meters above the surface of the Earth? So from the physics data table on your formula sheet, it's going to be 5.98 times 10 to the 24 kilograms. So that's right here, right? Mass of the Earth. And R is going to be 6.37 times 10 to the 6 meters. The new distance must be measured from the center of the Earth to the center of the person. So we can't just say that they are 1,200 meters above the surface of the Earth. As soon as you see a question worded like that, you should, like, alarm bell should go off that you're like, oh, no. It needs to be from the center of the mass. So if I'm talking about, some guy up here, I don't want this distance from there to there. I need the distance from him to the center. That's where we measure things when we're talking about their gravitational attraction. So what we got to do is say that the radius between these two is going to be the radius of the Earth, so that, plus their altitude, so plus how high they are above the Earth. So when you add those two together, you get this. That has to be what goes into our equation here. And now just plugging in the numbers, you get 979 newtons. So you can lose weight if you just go up in the air. You'll actually weigh less. But your mass will be the same, right? All right, so example 4 here says if the attractive force between two masses is that, so that's our force, and the distance is 50 meters, what's the mass of each object if one is 3 times more massive than the other? So what we have to do here is figure out what the relationship between one mass is and the other. So M2 is going to be 3 times M1. And the reason why that's important is because we have 2 things to solve, right? I can't just solve for 2 things in an equation. I can only solve for one thing at a time. So what I'm going to do is rewrite this like this. And what I've done here is 3M1. That's M2, right? I've just replaced M2 with 3 times M1. And the reason why we did that was because now we're dealing with just M, right, or M1. I can solve for M1 fine now, right? So now that it's written like that, I've got M1 and M1 on the top. They're being multiplied together. So M1 times M1, that's M1 squared. So that looks like this one. Now, if you rearrange that, you get M1 is equal to the square root of FG squared over 3G. Put all your numbers in, and then I get M1 is equal to 1.06 times 10 to the 4. Then all you got to do is go back up to this equation and then solve for m2. So m2 is equal to 3 times m1, so we just had to multiply that by 3. So I'd like you guys to go ahead now and read this using equations to guide as a guide to thinking. We've kind of talked about it as I was going through here. I already kind of talked about why that might be. Yeah. I do, though, want to go through this example 5 type of question. But I just looked, and we have one in the practice problems anyway, so I'll skip that one right now. And I'm just going to let you guys read through this gravitation, the big idea thing. So I'm going to end that one there, and I'll carry on with the practice problems in the next video.